So, like, I thought it was done.
Yeah, so it's more change of plan. So Bar couldn't make it today. So I get the pleasure to talk about Semurings. And actually enjoyed that a lot, but I have too many slides because I enjoyed it so much. But this is all Val's invention, Val's creation. I just like it.
Yeah.
Val is going to come on Thursday and talk about his latest passion, which is applying Semurings to first order logic, where you have negation, big challenge with negation.
Yeah. Have you been working on any more data logical stuff? Is there been follow-on work doing?
No.
Has you solved all the problems, or do you think there's like big
No,
questions left there?
I think there are big questions. To be honest, I think you're looking more into the interesting questions with Joe into these distributed settings. Because beyond that, the issue is Semurings. You need like a specialized Semurings for each application. And there aren't that many, so I don't have a good intuition how to generalize this. If you have an application, here is the Semuring to use. I'm not there.
This is a question like what language interface?
Yeah, I think that's the best way to phrase it.
Yeah.
Which becomes a compiler question and the static analysis question. And this is not my expertise. This is what Max is doing.
Yeah, I guess like what like stuff like CRPs does is say like explain really well to the developer what a Semurring is and let them define their own functions that satisfy those requirements, or give them a library of Semurings. Right, that's what it is for Linus's, right? But you can do it for Semurings as well. So like here's a library of Semurring operations. Like you can write your Python program using this library.
I see. So you do require the user to explicitly define the Semurring either directly or as some existing
Or consume. Yeah, but yeah, it's like kind of at their own risk with whether they are kind of correctly understanding.
I still need to read your Sigma paper, your upcoming Sigma paper. Yeah, it's too many things to do.
Yeah, yes, a good problem to have.
Can somebody check Zoom if you see a clean screen like this, not covered by good, excellent, thanks, Chris. Should we start? Yeah, let's start. So you might be surprised there is no Val Tannen here. So he had to cancel it. He's actually giving the CARP lecture next Tuesday, and he's getting the slides and busy doing this. So he will give a lecture on Thursday on more advanced applications of Semurings. So it's actually my pleasure to give you the introductory lecture on Semurings, which I like so much. This is all Val Tannen's work. I mean, he didn't invent Semurings, but he essentially showed us how beautiful this extension of relational databases is to Semurings. And this is something I adopted and like so much. As a result, I have too many slides. So please interrupt me if I go too quickly. It's important that we go slowly. We can always continue next week or sometimes if we don't finish. So this is the plan for today. We will talk about the definition of Semurings and k-relations, and we will discuss only the positive relational algebra. Semurings do not support negation. And Val will talk on Thursday about how to extend Semurings to give the semantics to arbitrary first order logic formula sentences, even with negation. And again, it's a beautiful mathematical development. A lot of material though goes here, and the definitions and the many applications and many ways to look at semurings and their interaction with the relational data model. And that's my goal for today. If we finish, fine. If we don't finish, we can continue next week. Good. So let's start by discussing semurings. So why semurings? Here is how to think about this. If you think about a relation and the relational data model, a tuple is either in the relation or it's not. This is a yes/no statement. The tuple AB R of A, the atom R of AB is either true or it is false. But in many applications, you want a more refined information about the presence of that tuple in the data in the relation, or you might even have some additional semantics that you want to give to it. For example, you might want to say that the tuple AB occurs 5 times, and maybe say CD occurs 0 times. This is back semantics. Or you might want to do linear algebra, which is like saying that the entry ij of a matrix, and these ij's, they don't necessarily need to be integers. They could be some values. You want to say this value is minus 0.5. Again, something we could capture if we have the right abstraction. I'll show you a cool application about security. And the original motivation, this is what Val drove to, what brought Val to semurings. The original motivation was to capture provenance. Provenance is a way to explain how a tuple in the output was derived from the input data. And the same semurings framework also allows you to capture this. So this is the motivation for semurings. It's an algebraic framework that can capture all these scenarios. Good. Definition number 1. How many people here know what a monoid is? Okay, not that many, so this is good. It's a good thing that I have this slide. A monoid, think about algebra. Think about an advanced class in algebra. They will teach you that a monoid is a tuple consisting of a set M, a binary operation written star or circle, some binary operation, and an element 1. This binary operation, I use circle, is binary. 1 is an element, and there are 2 requirements. The operation is associative, and 1 is both the left and the right identity for the multiplication of the operation of the monoid. Okay, you can already think about various monoids, and I have a slide on the next slide. It's an abstract concept. It's a mathematical concept. The monoid is called commutative if the operation commutes. If x times y is the same as y times x. I'm saying times, but it doesn't mean multiplication. It can mean addition, can mean anything. And the monoid is called a group if every element has an inverse, both the left and the right inverse. How many people here know what a group is in mathematics? Again, not that many. So groups are extremely well studied in mathematics. It's a huge branch. There is an extremely simple concept. This is what's beautiful in mathematics. You start with a very simple concept, and you discover that there is so much you can say about it. So a group is just a monoid where every element, x, has an inverse, both to the left and to the right. Quick exercise proves that the inverse is unique. You can't have 2 inverses for the same element. And when it's unique, it's usually denoted x to the power minus 1. That's the inverse in the group. Okay, good. So these are monoids. Simple examples. For example, the real numbers with addition, the real numbers with multiplication, the set of matrices, n times n matrices. You take 2 matrices, you can multiply them and get a new matrix. We have an identity, which is the identity matrix. Yeah, of these 3, which ones are groups? Is this a group with addition? Of course, yeah. Minus x is exactly the inverse. Is this a group? No, why not? Because 0 is the exception. 0 doesn't have an inverse. Okay, so you see how it goes. The set of permutations forms a group under composition. This is not a commutative group. I said a group, and it's indeed a group. Here are two things that we might use. The set of subsets of in universe omega forms a monoid under intersection. You take two sets, you intersect them, you get a new set. The identity is a bigger set, is a set of the entire universe. You can replace, you can take the union, and then the identity would be the empty set. Are these two groups? Are they groups or are they just monoids? Can you find an inverse, for example, what am I doing? For example, for union, can you take a set X and union it with something to get the empty set? Never. So they are not groups. Good, cool. So this is monoid, semirings. A semiring is a tuple that has two operations. Is an algebraic structure that has two operations, the addition and the multiplication. Addition forms a commutative monoid with identity denoted 0. Again, this is an abstract element that doesn't need to be any number 0. Multiplication forms another monoid with identity 1. Plus has to be commutative, multiplication not necessarily. And there are two more requirements. Multiplication distributes over addition. So this means that x multiplied with y plus z is what you expect, is x times y plus x times z. And since we don't know if this is commutative, in general it's not, we also need to write the distributivity in the other direction. Y plus z times x is yx plus dx. And the last axiom is that 0 be absorbing, sometimes it's called annihilating, which means that if you multiply anything with 0, you get 0. Again, terminology, S is called a commutative semiring if multiplication is commutative. All the semirings that we use in this framework of extending the relational model to semirings will be commutative. And you might have heard about rings and fields, and they are semirings where you also have an inverse for addition or also an inverse for multiplication. Okay, so we don't need them, but this is a connection you can make to mathematics. So semirings, commutative semirings are the object of our study. Quick examples, I have too many. The most important one are the Booleans. The 0, 1, they form a semiring where OR is the addition and AND is a multiplication. The real numbers form a semiring, the natural numbers form a semiring. The set of matrices, they form a semiring. The set of n times n matrices. Yeah, because we have distributivity, that law applies. The set of subsets, if we include both union and intersection, then we get a semiring. Here is a really cool one. It's called the tropical semiring. And it goes like this. The elements are all the non-negative number, all the positive numbers, including 0, and also infinity. The addition is minimum, and multiplication is plus. Very strange. Here is how to think about this. The tropical semiring is used to find to describe, if you want, the cost of the minimum cost in a graph of a path in a graph. And it goes like this. If you have a path and you want to concatenate it with a second path, how do you combine their cost? You need to combine this in the semiring, you combine this multiplicatively. But when you think about how you combine the cost of two paths, you add them. This is why the multiplication in this semiring is plus. But if you have two alternative paths between x and y, how do you combine them to get the best path, the best cost? You take the minimum. Yes, this is why the addition is minimum. It's a very interesting semiring. It turns out that I didn't we use it in the slides today, but this is one of the poster child of semirings for K-relations. Good, so these are semirings. So again, a quick summary of semirings. This is a topic that belongs to algebra. You'll find this described in textbooks on algebra, not in serious textbooks, because there isn't much you can say about semirings. You can say a lot more about rings, and especially about fields. So if you take by graduate level textbook on mathematics, in algebra, you'll find fields and rings, very little about semirings. But we are interested in semirings for the reasons I mentioned earlier. And in most cases, our semirings are not rings. They are things like the Booleans, which doesn't have an inverse, or the natural numbers, or the tropical semiring, and they are not rings. We only consider commutative ones. And this is important for you to not get confused. The abstract operations, we need to write them somehow to emphasize that they are not the standard plus and the standard times, but they are very cumbersome. So we often choose to write them as plus and times, with the understanding this is not the plus we know, it's not the times we know, it's an abstract operation in that semiring. So then this semiring operation will look like this, x squared y plus 3z. How do we read this? What is x squared? X squared means x times x. Yeah, so x squared y is x times y. And plus, what is this 3? There is no 3 in the semiring, but by 3 we mean 1 plus 1 plus 1. The identity added up 3 times. And if you apply distributivity here, this is the same as saying z plus z 3 times. This is what 3z means. Yes, Connor.
So there's these examples of semirings, they're like connecting them to database theory. Were they being used elsewhere before they were kind of discovered in database theory and other branches of computer science or other fields?
Absolutely. So the semirings have been studied extensively in the 70s, probably was also starting with late 60s, because they capture, they are a nice abstraction to generalize several family of algorithms, like finding the shortest path, all pairs shortest path. The matrix inverse is also described as a semiring. Trying to think about others, right? Automata theory. When you convert an automaton into a regular expression, this is something that you can describe in a non-commutative semiring. So they are a beautiful concept to generalize several known algorithms. The application to databases that started essentially with Val Tannen's paper much later in 2007. And we have a slightly different view of semirings from this direction. That's what I want to say. But you're right, they were studied and connected to various aspects of computer science way before the application to databases. Okay, any more questions about semirings? Good, cool. So let's talk about their application to databases. And the term used for that is K-relations. So again, the motivation is the same as I mentioned before. A standard relation associates to each tuple a Boolean value. It's 0 or 1, either present or not present. We will replace the Booleans with some fixed semiring K. And then we call that relation a K-relation, where each tuple is associated with a value in that abstract semiring. Okay, so let's see the formal definition. This is the definition from the original paper by Green, Karnoub-Barakis, and Tannen. A K-relation of some fixed arity M is a function from all the M tuples, and there are infinitely many, into the semiring, such that the support is finite. The support of this function is defined as being the set of tuples which are not mapped to 0. 0 means absent, so for us, they don't contribute. We care about the finite set that are present, that are non-zero. Okay. So here is an example. This is a Boolean relation, and you see how I associated Boolean values to the tuples. And there are infinitely many tuples. All the others are mapped to 0. How big is this relation? How many tuples do I have in this relation? What is the cardinality based on the person? How many tuples do you need to store on disk? 2, right? 2 tuples, because you only need to store Alice in San Francisco and Bob in Seattle. This is not present. You can erase it. You can show it or you don't show it. It doesn't matter. It's everything that we don't show is mapped to the value 0.
Quick question.
Yes.
Is this some sort of generalization, or like not generalization, but like a way, an equivalent of integrability?
Is this equivalent to what, Brace?
Is this some sort of like equivalent in this setting to integrability, this finite support constraint?
Integrability.
They can sum across this, like you can actually do a sum across the whole thing, and you're going to end up with something finite.
It's the same, yeah. It's the same definition. If you think about the probability space, the support is the same thing. It's a set of outcomes that have a non-zero probability. So it is related. Integrability is slightly more general because you don't insist on the support being finite, but you insist on the sum or the integral being finite. So that is a slightly more general concept. Okay, I can imagine
Gotcha.
an
Thanks.
infinite relation with infinite support, for which the sum of the tuples, if there was a notion of computing that infinite sum, still converges. But here we
Yeah.
Yep. But here we insist on a finite support. Good. So
Gotcha.
my point is here. We just changed from Booleans to natural number relations, and now we capture back semantics. Yeah, of course, in practice, you can store Alice San Francisco 5 times, or you could simply annotate this tuple with the fact that it's stored 5 times and to capture back semantics. Questions to you folks. How do database systems store bags? Do they store them like this? Alice San Francisco, and then there is another information there that says 5 times? Or do they store this tuple 5 times? Chris knows. How it depends. Okay. Tell us, how does it depend?
Lots of analytic databases is just like this repeats 5 times or 1,000 times or 1,000,000 times. Per column. But what's called to EDNS, which is still the same version.
Okay, for people on Zoom, so Chris says that for data analytics, several engines actually they do use a smart representation where a tuple is annotated with its multiplicity. But standard SQL engines, when they compute a query answer, they just don't care about identifying duplicates. They just keep duplicate tuples and they worry later on about eliminating them. Okay, and my last example is if you have an R relation, it means that each tuple can be mapped to a real value. And this looks pretty much like a tensor. This is what Grace is working on. So a tensor is an R relation. A sparse tensor, I should say. A sparse tensor is an R relation. This is what's cool about K-relations. It's a very simple and natural extension of the relational model to a concept that is kind of open-ended. You can capture anything you want as long as you have the right semilink. Okay, why do we care about the semilink? I could annotate this with anything I want. Any ideas? Where are we going to use the operations plus and times? Yes?
For queries like joins and other operations.
Perfect. For queries, the plus and times, they give us a natural semantics for the queries that we know and love from the relational data model. So this is where I wanted to show you the story. We have a query in the relational algebra or first order logic, and we know how to compute it in the standard semantics. We have an output, which is another relation. Now, if these input relations are not standard relations, but they are K relations, then we want the output to the query to also be a K relation with some nicely defined semantics. And we can do this in a very simple and principled way. Whenever we had conjunction, we replace it with times. Whenever we had disjunction, we replace it with plus. It turns out this is all we need in order to give semantics to queries in the positive relational algebra. No negation. Positive relational algebra, it is equivalent to unions of conjunctive queries. And I'm going to show you both definitions because they're both very simple and it makes sense to go over them. So which operation is missing from the positive relational algebra? There are 5 in total. 1 is missing. Which one is missing? Difference. Difference is missing. So we only have join, selection, projection, and union. So we need to define what they mean over K relations. So this, I need to unfold the notation here. Remember that a K relation is a function from tuples to values in the semi-ring. So if I want to define the join, I need to define a new function called the join that takes as input a tuple and gives me a value in the semi-ring. Now, R and S themselves are functions from tuples to the semi-ring. So how do I define this? What do I write here to define what the join means? You want to try?
I think we should break the tuple into 2 parts, right? And we use the R times, and we check how many occurrences of the first half of the tuple in R and how many times the second half of the tuple occurs in S and what comes together.
This is perfect. So we need to break the tuple to T in half. He said in half, but of course we know we need to break it into the attributes from R, into the attributes from S. Check how many times or what is this semi-ring value that R gives us for each fragment of the tuple, but the semi-ring value of S that S gives us, multiplies them, and that is the answer. Very intuitive. So I'm glad that you saw this. For selection, you might think it's easy. You just check if the predicate is true, and you return 0 or R of T otherwise. But there is a clever way that was there in the original paper. I'm going to show it to you. Instead of checking here, we're going to multiply the old value, R of T, with an indicator variable, indicator function. The indicator function does a case analysis, and it's independent of R. That's the beauty. So the indicator function takes this Boolean value, the predicate, and if that is true, then it returns the 1 of the semi-ring. And if it's false, it returns the 0 of the semi-ring. And this is what we multiply with tuple T. Okay. Projection. This is interesting. How do we define projection? Yes?
You have to do a sum over all the cardinalities for values and mentioned.
You really got it. We need to do a big summation because when we project all these tuples, they collapse to a single one. And we need to add their annotations, their semi-ring annotation. And the last one is union, which is obvious. It's just a summation. This is the positive relational algebra over semi-rings. So I have here an example, but you got it so well, I should go quickly over this. So the way to read it is the annotations are X, Y, Z. This has annotation UV. When you compute the join, you can see the result here. So what are the annotations here? We just need to multiply them. Yeah, and I wrote the shortcut without circle. Yeah, so this means multiplication in the semi-ring. For a selection, we just multiply with 0 or 1, depending on whether the tuple and the predicate is true or not. And of course, everything multiplied with 0 by the absorption rule or the annihilation rule, this is 0. So we might as well delete these tuples from the output. And it's the same semantics. And the projection, as you pointed out, here we need to add. A1 is easy because A1 only occurs once, but A2 occurs many times. And we need to add their annotations. And this is the annotation that we store in the answer. Hard not to love K relations. They have this very natural extension to the positive relational algebra. Okay, so now let's come back and see if our K relations are the B relations, the Boolean ones. We apply the previous definition. What does a query compute? It's a standard interpretation under set semantics. Notice set semantics because the Booleans, they satisfy this rule: x plus x is equal to x, idempotent. Okay. What happens if we interpret them over natural numbers? What do the queries compute now? Back semantics. So we compute the queries under back semantics. N is not idempotent. X plus x is not equal to x. We just add the multiplicities. Okay, good. We can define the same semantics directly using the syntax of unions of conjunctive queries. So to remind you, a conjunctive query has some variables in the head, existentially quantified variables, and then a conjunction of many, many atoms. And what is its interpretation over K semirings, over K relations, I should say. So it's a sum. Existential quantifier becomes a big summation. And I think the details are not that important. I got them right, but yeah, the details are not super important. We need to sum over all the tuples in the domain. We don't care if this is an infinite summation. And the details are actually important because what should this be?
Plus.
This should be a plus, typo. Yeah, so it should be a big plus. Existential quantifier means a big disjunction. So this needs to be translated into a big summation. And inside here, we have the product of the projection as before of that. And here again, I missed the indices on the projection on Z1, projection on Z2. Yeah, I have some typos here. Okay, good, cool. This was for a single conjunctive query. If we have a union of conjunctive queries, we just add up the individual ones. Very simple. So the semantics is super simple. We just replace or and with plus and times. That's all we do. Yes, Connor.
For selection, is there any notion of like if you imagine like where clauses in SQL, like extending them to use the operations of the semiring in some way? Like if I want to say like these two tuples, least up or bound, is this constant from the semiring? There's like the way we talk about them is just like you're marking true and false in the table.
Yeah, so this is the only way I thought about translating the web predicate. You take that predicate, it's a Boolean predicate, that's a true or false for each combination of tuples, and then you multiply with the indicator variable. What you're thinking of is something more advanced, where you want to interpret the predicates in a smarter way. And, yeah, I don't have any thoughts about that.
I think that does touch on an interesting, this is something, a question I've had about this sort of framework is that inside, if you think about how K relations work from like the SQL perspective, there's like restrictions on the things you can say about the semi-ring value, right? Like, you know, in your where clause, you must be taking like the min or whatever, yes. Right? Like, so one thing that I'm interested in, for example, is like joining, like, you know, suppose your semi-ring is actually the same value type as, you know, some column somewhere else, right? Like joining and doing an each join or sort of other sort of join there. Like that's not super well addressed. Like, you know, as long as you fit within like, you know, doing exactly simmering operations, it works, but how to mention that, it's sort of unmentionable outside of that context, which is interesting.
So to summarize for people on Zoom, so Max had a beautiful comment that the answer is that a complex where clause in SQL, the way we, according to our discussion, gets translated into a very naive semi-ring operation. Takes that complex clause and just map it to either 0 or 1. But you often want something more refined, something that where the complex where clause actually exploits a semi-ring structure in an interesting way. And I don't know how to do this, and you know that could be a more advanced, probably something more creative, some research problem how to do this in an interesting way. Okay.
It
Yes.
kind of relies on being able to like propagate the annotations very efficiently. Right.
You also need to propagate them. Yep. And I have something to say about this. That was the original motivation of Providence. I want to show you two applications. One is to sparse tensors, and the other is to security. So sparse tensors are relations where the tuples are annotated with real numbers. So let me try to convince you. Here is a matrix, and it is sparse because you have many zeros. You can represent this as a relation by listing only the rows and columns that are non-zero and annotating it with the values, with a real value, which is the value in the matrix. Yeah. So, but by the way, this is a kind of one of my favorite exam questions for the undergraduate class, giving them questions to multiply matrices, add them and stuff like this. So let's do this. Let's look at transfer operations, how they correspond one-to-one to conjunctive queries. For tensor operations, there is a cool, how should I put a trend in programming languages? It's called Einstein summations, and some of you are probably much more experts on this than I am. I know that PyTorch and TensorFlow and another one, they have been extended with Einstein notations. They are just conjunctive queries if you interpret them over R relations. That's what they are. So let me show you an example. Here is a conjunctive query that, as we read it, computes a join of A and B. But if you interpret this over the reals, then a conjunction becomes multiplication, existential becomes summation. And what does this compute? What I asked my undergraduates to write on the exam. This computes multiplication. Yeah. So if A and B are sparse representation of matrices, then they can also be dense. But if you represent them as relations, then this conjunctive query essentially corresponds to matrix multiplication. Okay, so this is what einsums do. They there is a syntax which is slightly different from the syntax I'm showing you here. So read the manual, but it's a simple syntax that also drops the quantifiers. This is the Einstein part of the Einstein notation. You drop the summation, and we did this already in conjunctive queries, right? When we write Q of X and Z, and I don't show here the existential quantifier, I always remind you, remember that the other variable is existentially quantified. Same with Einstein notation, whatever we don't mention is summed out. For example, transpose, by the way, all these examples are from a beautiful website here on einsum notations. This is transpose. This is summation. You see, I say S, the scalar S is AI of I and J with the understanding that we have to sum out I and J. Apparently, you can write this in PyTorch. Am I right? Did anyone try? Yeah, good. You can sum up just one row. For each row, you compute the sum. You can do the dot product. You can do the outer product. What else can you do? This is cool. You can do, they call it batch matrix multiplication. which means that you have many matrices indexed by this M. And for each M, you want to multiply the corresponding matrices, and you get a new string of matrices. Cool stuff with Einstein notation. Good. This was application 1. Let me show you application 2. This is super cool. Access control. So the classical traditional access control comes in 2 flavors: discretionary and mandatory access control. Discretionary access control is what you know from Unix. For each user and each resource, like each file or whatever, there is a permission. This user is allowed to read this file. This user is allowed to write that file, and so on. This is discretionary access control. Mandatory access control is what you use in the military. There are clearance levels, like secret, top secret, and so on. They are ordered, and each document has a level of security. Each person has a clearance level, and then you compare them and you see if you can read them or not. So let me show you how this works. There is an access control semi-ring, which looks like this. The domain consists of all the security levels. Public is the smallest one. Confidential, secret, top secret, and no such thing. Okay, you remember the joke with NSA? What does NSA stand for? No such agency. That is 0. Yeah, apparently it was so secret at the beginning that the government didn't want to talk about this. We don't know what you mean. So this is 0. Now, how do we combine things? So let's take this query here. We have a set of pictures, and they have their own security level. But these pictures, they belong to documents, and the documents, they have their own security level. And now, so you see, picture 1 is secret, picture 2 is top secret. Document 1 is confidential. Document 2 is what? Document 2? No, document 2. There is no such thing. And the many relation between these two, this is public. You can figure out which ID belongs where. So what I want all the pictures. I want to return all the pictures, but I'm also joining all the way to the documents. So what I'm getting are the 2 pictures. Question is, how should I annotate P1? What is the clearance level for, or the security level for P1? P1 is secret. It occurs only in document 1. I need to read document 1 to get it. Document 1 is confidential. How would you annotate this picture? To see the picture, you need to look in the document. The picture and document, they have kind of their own security levels. So what do you propose? Sorry? You would put a secret. Let me check this. Secret is stronger than confidential. Absolutely. So you need to have a secret security level in order to read document 1. What about document 2? For document 2, I have a choice. I can either read it from document 1 or from document. Sorry. The question is, what about picture 2? For picture 2, I have a choice. I can either see it in document 1 or in document 2. What would be the security level for picture 2? It's confidential. You are fired. Not confidential. Why is it not confidential? I'm kidding. No. Why is it not confidential?
The picture itself is top secret.
Because the picture itself is top secret. So that is the answer. So how do we combine them? How do we combine security levels under a join with what operation? You can read it from the slides, but it's so natural. How do you, sorry? Yeah,
Sorry, Max. Yeah.
You take the max, the highest one. Yeah, you need to have both of them. So you look at the highest security level. How do we combine them under alternative?
Yeah.
You look at them. This is why here we have min and max. Beautiful semi-ring.
Like a simpler version of the tropical scenario.
It is actually, yeah. So the tropical semiring also has a minimum. It's like when you have two different paths, we take the minimum, but when we combine them under join, we add them, and this is no longer idempotent. If you move in a loop, and then you add and add and add, you get longer and longer paths. While here, if you move in a loop, we don't care. It's the same security level. Good, cool. So that was my introduction of K-relations. So what to take away is what a powerful and simple at the same time abstraction this is that allows us to talk about so many other applications. That is the beauty of semirings. One thing I didn't put here is that you can take any set you want and annotate your tuples from that set. But the semirings kind of it's a sweet spot between being an arbitrary annotation and also the ability to interact with joins and with unions. So we can compute queries over relations annotated with semirings. Now, if you have something more complicated than joins and unions, then the semiring won't help you. But that's why I say it's a sweet spot. It's not a super complicated concept, yet it's powerful enough to support at least a relational queries. Yes, Max.
So the semiring, I can see how it sort of helps us semantically, right? Because we have this nice syntax where you're talking about functions and the semantics make sense, but semantics also sort of tell us how we could implement this using SQL for for any system with aggregates, right? Like if you just have the ability to write the aggregate, the semantics more or less spelled out like how we could have taken our join and our nice syntax and written it in some uglier but still the same thing in SQL with aggregates. Right. So what is if aggregates are our execution model, like what are semirings buying us? Because we could talk, the aggregation model is more powerful. We could talk about aggregating over things that are not semirings, for example, and we can do the joins and the wheres that we were discussing. So I think one thing that I'm curious, and maybe we'll get this in provenance or optimization, is from at the execution level, what is semirings buying us compared to just general aggregates?
Yeah, so to summarize Max's question for people on Zoom, we could always implement the semiring operations with what we already have in SQL. We don't need to extend relational engines with semirings. And this is true, it's correct. So we don't get an additional expressive power, but we get an abstraction that allows us to, and indeed, gets to optimizations. It allows us to easily understand how to deploy optimizations when we are dealing with a semiring, which is more obscure to see if the semiring operations are implemented directly in SQL. That is just an abstraction. It doesn't give you more expressive power, but it clarifies and allows you to think with more clarity. IMSAM. So it's amazing that these are so popular in ML today. So they are implemented in NumPy, TensorFlow, and in PyTorch. But the syntax is not exactly what I show you. It's very similar, so we need to check it. And I should mention that the original motivation was not to capture tensors and back semantics, but it was to capture provenance. So I need to discuss provenance. And when Val comes on Thursday, he might be biased to talk more about provenance than to talk about other applications of semiring. So let's talk about provenance and the beautiful concept of provenance polynomials. So what is provenance? Imagine you run a query over a standard input data, your basic relations, and you look at an output tuple, and you ask the question, how did this tuple get into my answer? And the provenance aims to answer this question. It's not even clear what an answer should be for why did this tuple get in my answer, but this is what the research on provenance aimed to do. There were many variants proposed in the literature. It was quite confusing in the late 90s and early 2000s. And everything became so much cleaner once this paper came out in 2007 on K-relations, And the observation that all the previous proposals can be captured as specific semi-rings that can express provenance. That is the high-level story. So let's talk about polynomials, because this is a way to capture the most general form of provenance. I should have had a slide on polynomials. Let's start from here. So fix some variables, x1, x2. N of x means a set of polynomials, of multivariate polynomials with variables x1, x2, and so on. You can write x1 squared times x2 plus, you can only write plus, no minus, and otherwise any polynomial you want. Here is how we use this, and this is a semi-ring. We can add polynomials, we can multiply polynomials. There is a 0, the constant 0, there is a 1, the constant 1, so this is a semi-ring. To get to provenance, start with a fixed database instance and annotate each tuple with a distinct tag. This is called an abstract tag, because you want to trace how these tuples get propagated through query evaluation. So it's best to create a distinct tag for each of them. Sometimes you can argue you want the same tag from 2 tuples, but let's imagine that these are distinct tags. Once you do this, every relation is annotated with one of our variables. So we think of it as being annotated with a polynomial. It happens to be a very simple polynomial consisting of a single variable, but it's still a polynomial. So now compute the query over these nx relations. We know how to do it. Joints become multiplication of polynomials, and existential quantifiers or projections, they become these additions of polynomials. And now look at the output tuples. They are annotated with some new polynomials. Now they are interesting polynomials. And these are called the provenance polynomials of those output tuples. That is a high-level story. So let's look at the details. So this is it's a very complicated example directly from the paper, from the original paper. There is a single input relation and a super complicated query that is a union of 2 conjunctive queries. You know what? I'm not going to read this query. I worked hard on it to make sure it's correct. It is from the paper, but they write it. They actually have a typo over there. Yeah, so it is correct. It does something interesting. It only returns 2 outputs, A and C. And now we apply our technique and we compute the outcomes. And we get these polynomials. And now comes the interesting thing. What do these polynomials tell us about the provenance of these tuples? What can you say about AE? Why is AE here? What was used to produce AE? And you look at this provenance, and you convert this into English. What is this provenance XY tell us? To produce AE, what did we use? Yes?
Tuples marked as X and Y.
The 2 tuples marked as X and Y. This is what we used. Very clear. What about AC? What did we use to produce AC? Yes?
We use a tuple marked as X twice.
We use it twice in 2 interesting ways. We joined it with itself. So this is what we got X squared. And we use it twice. And the reason we use it twice because it's a union of 2 conjunctive queries. So the first one produces this AC by joining this tuple with itself. The second one produces the same AC again by joining the tuple with itself. So this is why we get it twice. And similarly for the others. Yeah. So so AE is derived from X and Y. AC is derived in 2 ways. DE is derived, as you see here. That is the beauty of provenance polynomials. You compute them, and then you can read directly what they say about the provenance. Yes.
So we don't actually need to use like the natural numbers as a base
thing. You can just interpret the variables as like uninterpreted sums, right? Like formal sums and multiplications. Because the coefficients are kind of like short, you can think of it as just shorthand as we discussed before, repeated. So you don't actually need the whole natural numbers, right?
You don't need the whole natural numbers. What you're saying is true in a subtle way. So you can interpret these polynomials in any semi-ring. And the formal statement, which I have in a few slides, is that these polynomials, they are universal, exactly because you can interpret them in any semi-ring. But you're right, intuitively, you can think of this xy as being the product in some semi-ring. It doesn't have to be in the natural numbers. But if you commit to this one object, which are the polynomials over the natural numbers, then if you compute the query over in this one semi-ring, then you get these provenance semi-rings, which are by definition in the natural numbers. Yeah, but hold your thought, because this is actually a very important observation. What did people consider before? So they struggled with the question, should we distinguish between conjunction and disjunction? So there is a notion of provenance, it's called Witch provenance, that doesn't care if you use the same two tuples and join them, or you use them as alternatives. You just return the set of all the tuples that you have touched during query evaluation. And that was one kind of provenance. Another question was, okay, so we distinguish between union and joins, but do we have idempotence or don't we have idempotence? Again, an interesting distinction. Do we have idempotence for multiplication? Is R joined R? I wrote it as intersection, but you should think of it as a join with itself on all the variables. It is the same as just R. Yes, Chris. Yes.
Which provenance also included tuples that weren't present? It was necessary that the tuple was not present in order to.
This is a difficult question. So the question is how do we describe the tuples that should not be present in order to have our result? Yes. And this is difficult because in semi-rings, we don't have a natural way to compute difference, to compute negation. This is what we would need. Much of the research has been done trying to circumnavigate this. Weiss's proposal that he's going to describe on Thursday is the most elegant one. He avoids having to deal with difference. But yeah, this is a very interesting question. There was a paper which is very well known because it has a funny title, the why and why not provenance. Why is what you expect, why is the tuple present, and the why not is not exactly what Chris mentioned, but it is the question, why didn't you give me this answer? What was wrong? It's a systemish paper by Jagadish. Yeah, he didn't solve the semi-ring question. But that is the essence of the question, is that we don't have difference in semi-rings. Okay, so what else? Great. So this is a picture from Weiss's slides, which kind of captures in one slide all the landscape of the various provenance proposals. It's actually very instructive to read it. Start from the top. This is kind of the universal provenance. These are the provenance semi-rings. So you can see that here a provenance can look something like this. We have a complete polynomial. One way to simplify this and to get one kind of provenance, which I forgot how it's called, is to use, and this gets again to your discussion, to interpret these polynomials over Booleans, which means that the coefficients are no longer 3 and 5, they are only 0 and 1, which means that 2 becomes 1, 5 becomes 1, so you drop the coefficients. And another way is to drop the exponents, to have x times x equals x. And then you get to a provenance that was called trio. You can drop both, and then you get to a provenance that's called y provenance, and so on. And this is the which provenance, which means to really kind of, collapse everything together and don't keep track of the alternation, disjunction, or conjunction. Okay, I really love this picture, and it's hard to draw. I got it from Val's slides. For people who worked hard to understand the landscape of provenance, this was like an aha moment. So now we understand how these things fit together in one single slide. Okay, good, cool. So that was my discussion about provenance polynomials. We're actually doing quite well, but let me know if I go too quickly. I'm happy to go back and revisit some slides. Now, a high-level comment. These provenance polynomials, they are fine-grained provenance. They keep track exactly of how the tuples were generated from the input. Real data science requires something that's typically called coarse-grained provenance, which is much harder to define formally. It's this desire to have to take a complex data science pipeline and annotate the answers with enough information that you can later on decide how this pipeline was computed. For example, which input files were used? What were the versions of those input files? What were the dates? When were those input data? When was that collected? What were the tools used in the pipeline? What kind of data cleaning tools did you use? Maybe they have different versions. You want to annotate all this information on your output. And this is not what the semi-ring framework gives us. Here you need standards, essentially, for these annotations. Okay, any more questions before we move to optimization? Yes.
I have a question. It's kind of random, but I was thinking back to the stuff we talked about on like incomplete databases and repairs. And I remember there, like, for repairing certain things, you want to, kind of do the best repair by checking like the minimum difference. And they ever use like cardinality of like projecting. So it feels sort of like a bag semantics type thing. I was wondering if there's any sort of similar questions you can ask where you use a different semi-ring as your sort of like metric. And
yeah, so the question is, can we use a better notion of repair, or a more refined notion of repair that applies to k relations? And the answer is nobody knows how to do this. But I should mention that for Kyon Kolaitis, with the Assignments Institute, he has exactly the same question on his mind. So can you what would be the natural way to extend the repair framework to k relations? What is a constraint over k relations? If I want to say this is a key, well, I can say it's unique, but maybe there is a notion instead of having a yes or no answer, this is a key or not a key. Maybe I have a semi-ring value that gives me the degree of keyness of that attribute, and then the repair can be interpreted as improving or improving over this degree. You get quickly the bug on database research. This is how we kind of get you into the community, because these are fascinating questions to ask, and with the right application, they can have big impact. Yes, Connor.
So the provenance polynomial is, think of it kind of like a log of all the operations you performed, like the joins and the unions over time that produce this tuple, and that you could do that without it being a semi-ring, like just some function operations. You could log all of them as a sequence of function operations on a bunch of inputs, right? Like the identities of the semi-ring are determining how compressed this representation of this log is, in effect. Like, does that make sense?
It makes sense. I'm thinking about this. I also want to repeat for the Zoom. So what Connor observed is that the provenance semi-rings, they are just a log of the operations done to produce an output tuple. This is correct. And the question is, are the provenance polynomials essentially compressed representations of this log? And that I'm not sure. I don't see, they are not the best compressed representation. You can represent you might be able to compress this even better by representing those polynomials as circuits, identify common subexpressions, use some kind of compressed circuit. People have looked into this direction. I don't think there is a definitive answer. But there are, if compression is your goal, then this is, you need to go beyond this, the standard normal form representation of polynomials. Also, I should mention that in addition to being a log of all the operations, the provenance semirings also gives you a disciplined way to combine these provenance operations. If I have one provenance for this tuple and a different provenance for the other tuple, when I compute their join, I know exactly how to compute the new provenance. I just multiply the two polynomials. And then you can simplify it, you can recompress it, whatever. That's what the provenance polynomials give us.
Similar question. So like, does the fact that like the distributive law of plus and times like do something for us for this polynomial?
Right. So the distributivity law might allow you to compress the polynomial. The polynomials, they only satisfy these two laws. I mean, the laws of the semiring. So you by applying these laws repeatedly, you might be able to represent the polynomial more compactly. Let's go to this, because that is exactly the next topic. These identities and the algebraic laws that the semiring satisfy. And the question is, how does this relate to the optimization rules that we already know for database systems, and that database systems already implement? Okay, so I should have put animation here, but let's start from here. These are the kind of rules that you expect to find in a standard database system, one way or another. It's often, they are not explicit. They might be hard-coded in the optimizer. They might be explicit as a base of rules, but they go like join is associative. Join commutes over union. You can push the selections down if the selection only refers to attributes in the relation R. Question number one. If we take the full relational algebra, standard set semantics full relational algebra, is there a finite axiomatization of this relational? Can I write down a finite set of such axioms? That's all there is. These are all the axioms that Max needs to use in egg in order to guarantee, well, if egg were to terminate, in order to guarantee that it can find all the equivalent expressions of a query. I wrote here, there is no finite axiomatization, and you should know why. Why is there no finite axiomatization of the full relational algebra with the 5 operations? What is the deep theorem that we know? We haven't proven it yet, but we will prove it. What is the deep theorem that we know about finite model theory? Trachtenbrot, that's the only one that we know. So somehow it's related to Trachtenbrot's result. If we had a complete axiomatization, then we could check if a query is equivalent to empty set, to false. If it's equivalent to false, it means it's not satisfiable. There is no database that satisfies it. Satisfiability is undecidable. Now, this does not immediately prove that it's not axiomatizable, but it does follow by the recursive, co-recursive argument. We know how to enumerate all the queries that are satisfiable. If we also had an axiomatization, then we could also enumerate all the queries that are equivalent to false, equivalent to the empty set. And then you can, by using these two enumerations, you can take any query and see if it occurs in one enumeration or the other. You can decide if it's satisfiable. So no hope to find a finite axiomatization or even any recursively enumerable axiomatization of the relational algebra. This is why database systems, they have their own secret sauce of what kind of rules they deploy. However, there is a finite axiomatization of the positive relational algebra. I'm thinking about set semantics. Why is that? Why is a positive relational algebra suddenly so much easier? What do we know about checking equivalence of queries? Homomorphism, exactly. To check equivalence of two conjunctive queries, you just need to find homomorphisms between the two. To check the equivalence of two units of conjunctive queries, it's a little bit more complicated. We didn't do too much practice, but it's there on the slides. You just need to check that for any conjunctive query here, there is one over here where you have one homomorphism, and conversely in the other direction. So this means that all we need to do is, starting with an expression in the positive relational algebra, we need to normalize it to get a union of conjunctive queries. So you just write down the axioms that you need to ensure that each such thing can be normalized, and you're done. This is a complete axiomatization. Plus, you need to write down all the axioms that you need to check for those homomorphisms, which is not that straightforward, but it's something that's doable. Okay, all this is over set semantics, not even back semantics. The question is, what are the algebraic laws if we want these queries to be interpreted over K relations? Okay, so this is where we need to examine homomorphisms and universal objects, homomorphisms not between queries, but homomorphisms between these semirings that we use to annotate the queries. And the homomorphisms are exactly what you expect. They are functions from one semiring to the other that commute with everything that the semiring cares about. 0 is mapped to 0, 1 is mapped to 1, addition is mapped to addition, and multiplication is mapped to multiplication. Quick question. Think about two semirings, the Booleans and the natural numbers. Booleans have operations and or. Natural numbers have operations plus and times. Is there a homomorphism from the Booleans to the natural numbers? No, why not?
Addition is saturating.
Addition is idempotent. So if you have x or x, this needs to be mapped to x plus x, but x or x is x, x plus x is not x, so we are in trouble. Is there a homomorphism of the natural numbers to the Booleans? Yes, what is that homomorphism?
All positives to 1.
All positives to 1, and 0 goes to 0. And that is a homomorphism. Do you see how we can get these kind of homomorphisms? Good, so why do we care about this? Because the polynomials, they play a very special role in this world of semirings with our homomorphism. They are the freely generated commutative semiring. It's a mouthful. How many people here know category theory? No, okay. It comes from category, but you don't need category theory to understand this. What this means is that take your set of variables x, and take any semiring you want, the Booleans, the natural numbers, the tropical, whatever, and find a function that maps every variable to a value in your semiring. Every variable is mapped to some value. The claim is that there is a unique way to extend this function to all the polynomials and map each polynomial into the semiring such that this extension is actually a homomorphism. How would you describe it? Unfortunately, I don't have, no, I didn't get a chance to write this. I should have added here an example. So let's suppose I have the polynomial x plus y squared. Just x plus y squared. And x is mapped to a value in the semiring. Y is mapped to a different value. Why do I map x plus y squared? To the value x, plus in this semiring, the value y times y. You just evaluate the polynomial over the values that this function gives us. This is what makes the polynomials universal. Okay. As a consequence, the following holds. Any identity that holds in all semirings has the following, I'm sorry, any identity that you can write over semirings has the following property. This identity holds over the natural numbers. This identity holds over all the polynomials over natural numbers. This identity holds in all commutative semirings. These are three equivalent statements. So to give you an example, here is an identity. I don't know if you can read it here. X plus y, x times x plus z plus y plus z is equal to, and I wrote down here something. I hope that's correct. You don't need to know semirings to check this. Yep. But my claim is that because this holds over natural numbers, this is where we need to check over natural numbers. And you don't, how do you check it? You just expand it. It's, you know, it's a high school. I hope I got it right. I counted here, there are 8 terms. Here I have 2 plus 2 plus 2 plus another, so I have 8 terms. At least I got this one right. I think it's correct. So this is an identity over the natural numbers. Therefore, it is an identity in all commutative semirings. So if you want to check an identity, if you want to hold in all commutative semirings, don't worry about all of them. Just check it in the natural numbers. And the consequence is that this extends to k-relations. An identity holds in the positive relational algebra over bank semantics, which are the natural numbers, if and only if it holds over all k-relations. Yeah, but this is over back semantics. What happens if we change to set semantics, which are no longer the natural numbers, they are the Booleans? Do we get more identities or do we get fewer identities than those that hold over back semantics and as a consequence hold in every case semiring? We get more, yeah, it's by definition because the ones in the back semantics hold everywhere, including the Booleans. What are the new identity? Give me an example of a new identity. Yes.
X squared equals X.
X squared equals X, which in terms of relational algebra becomes what?
Idempotent
Of times, of join. So you take an intersection if you want, but the correct term is join. Relation R joined with itself on all the attributes is equal to R. It's not true over back semantics because if you have duplicates, you need to multiply them. You need to square their number of occurrences. Good. So this is something to take away. If you want your optimizer to work over any semiring, all you need to do is to have an optimizer that works over back semantics. And I thought this is cool. This is also kind of hidden there in the original paper. It's one of their theorems. And it's actually if and only if they prove that if you want such a statement, then you need your K to be a commutative semiring. Yes, Connor.
Is it easy, given a set of identities, to find the equivalent of the natural numbers, like the general case polynomial? Consider them like here, the reason that the natural numbers of the like general case for the polynomials for all punitive semirings is because they capture exactly the identities of punitive semirings. And like for a full lattice instead of a set of punitive semiring, it would be probably the Booleans, I see. But
so I think the question you want to ask is as follows. If I want a more restricted class of semirings that also satisfies, for example, idempotence for addition or idempotence for multiplication, what is a freely generated semiring by a set of, all these are valid questions. They exist. So there is a general theorem, I think Birkhoff, but it's actually pretty easy to prove that no matter what identity you take, doesn't have to be semiring. There is always a universal algebra generated by a set X over those identities. So you can find it. The question is, can you describe it in a natural way? Let me ask a quick question. So we were here. So this is a commutative semiring. Suppose I want to generate a free semi-ring, which is not necessarily commutative. So I want to say, here is a set that depends on X, that is a freely generated semi-ring by the set X, with a property that for every semi-ring, commutative or not, I can extend the mapping from the variables into that semi-ring to a homomorphism from my semi-ring to K. What is that bizarre semi-ring? Remember, addition has to be commutative, but multiplication no longer needs to be commutative. Yes, Connor?
Matrix addition and multiplication.
No, I wouldn't know how to construct the matrices. I only have this set X. Think about it this way. To take X and Y, two observed variables. Is XY equal to YX? Yes?
Regular expression or something?
Yes. This is where you get you get kind of polynomials, but less than a regular expression. There is no star. Yeah, so it's like a regular expression, but without star. So you have monomials of the form x times y times x, which is not the same as x cubed y. Yeah, and you add them, plus whatever else.
What does addition mean? Is addition like the expression of like which non-terminal we choose?
Yeah, so these are exactly, it's a nice way to describe this, regular expressions without the star, star-free. Although star-free regular expression means something else as a terminology, but yeah, you know, there is a big open problem. Star-free regular expression means including minus. With minus, you can express some things that have a star, and yeah, it's a long story. So good, so that, I think we are already out of time. Let me just summarize. This is what I find super exciting. The fact that this simple abstraction of K relations, on one hand, they broadly expand the scope of what we can do with this concept of relational, of the relational model. And think about it this way. If you have a cost-based query optimizer that works for back semantics in SQL, you could, in theory, you could take this optimizer and deploy it to process any kind of semi-rings. For example, sparse tensors. This is something that Grace wants to do, to optimize complex tensor programs, tensor kernels. And you should be able to do this by deploying traditional query optimization techniques. Good. So is this a good time to stop right on time? I didn't get a chance yet to check your homework, but I will do it hopefully today. And a new homework is not yet posted. I still need to think about designing it. Thursday, we have Val Tannen. And at some point, I need to get organized about our final presentation. I want each of you to pick a research topic, a small research problem, and prepare like a 15 minutes, 10 or 15 minutes presentation. It's going to be a lot of fun, sometimes in early December. Good folks. So let's stop here. I used to know. Okay, finally.